even bidden.
Okay, welcome to the 9th lecture on multibody dynamics B after a long break, right? 3 weeks ago was the last previous lecture. So that gave us some air. And now for the last pieces of lead, de laatste loodjes. So today I'm gonna talk about rolling contact in a two-dimensional world, and we're gonna step out from a two-dimensional mechanics or dynamics to the three-dimensional world. But before we do that, we start, of course, with the quiz. Yeah. My Kahoot. And number 9, yeah. Classic. So there are 29 students in class, physically present. And I'm always super curious how many players we have in the quiz. "31 in class." Yeah? Okay. Okay, yeah, let's start. This is the old, forget it, doesn't matter. I should have changed it. 5 questions. The questions today are 60 seconds, and it's also for the live stream, so you only have 50 seconds, 50. And please discuss, I mean, I always say, convince your neighbor that you have the correct answer. And if you don't have a neighbor, seek a neighbor. I specifically said the number of constraint equations. I mean, you can think in 2D, I make one cut, but by making one cut, of course, you get in 2 directions, right? So I think that is the whole misunderstanding. I specifically say 4 constraint equations you have to make. Cuts as in, yeah. So it's 2, of course. And oh yeah, where can you do that? Either here at the support, then we have a nice open loop structure, or here at the support, or connected loose here. That's not so smart. Maybe here is a bit smarter. Then you have a single pendulum and a sort of a triple pendulum. I mean, there are various ways. Okay, Nathan, where are you? At home. Okay, Nathan, where are you? Yeah, very good. Well, I need not discuss. This is clear. By the way, this was an example where there are two answers out of 4 correct. That's what multiple choice is. There can be 1 or more correct answers. Okay, anonymous. This is a one from 3 weeks ago, with a little adaptation. Yeah. So I think 3 weeks ago the answer was RK3. Of course now I changed the assignment a little bit. At a local truncation area in Hoyne is order 3 and the global one is then order 2, and we see this order 2 in the media. For one unit here it goes down 2 units here. Okie dokie. Jody? This is again one from 3 weeks ago. With some slight adaptations, of course. But it shouldn't be too hard. Sorry. Yep, super. Okay, no discussion. Last question. So that's about the topic of today. And either you use your knowledge already on rolling contact, or you just use your mechanical insight. And please discuss with your neighbor. I mean, if it's very quiet in the room, I'm always concerned. Like, you have no clue what it's about, or... Think of your bicycle. Yeah, very good. Only 2 degrees of freedom. I mean, the machine can move, media, sorry. The machine can move back and forth, and you can do a steering motion, and that's it. That's all you can do. And it's a nice example of a very strange system, because in a kinematic sense, it's at 3 degrees of freedom. It's like, or actually 4. You can put it anywhere on the plane, 2 degrees of freedom, in any direction, 3, and you can put your steering assembly in any direction, 4. However, so that is about the coordinates. However, for the motion, you only have 2 possible motions, back and forth and steering. And that explains why you have to do parallel parking. I mean, when you found a parking spot, you cannot move your car in the parking spot. You have to do some strange maneuvering with backwards and steering, and yeah, okay. But that's exactly the topic of today. Nathan, very good. Save the results. Okay, show some feedback. I'm okay with that. Okay, and we're done here. We're done here. Then we go to the OBS, that's everything running. And then I go to the air server. Oh yeah. Okay. All set. Okay, that's good. I'm all All set. Yeah. So we're back again here. And this can go away. And this we can zoom up. Okay. So as I said today, two topics: rolling contact in a two-dimensional world, and going from 2D to 3D. I also want to do a small example with MATLAB, of which I will post the M files on Brightspace. So if you then feel like it, you can run them at home, and it's all about this rolling contact and non-holonomic constraints. Okay, so picture, for instance, that you have some rolling body, and it's easy to imagine that you have something like a wheel or a coin, and it has some angular speed, it has some forward speed, and of course this lives in a three-dimensional world, right? The thing can move anywhere with some speeds, and it can also tilt. Now, you can also imagine that, let's forget about the tilting, let's assume that the wheel is always upright. And if we do an upright wheel and we work only in a two-dimensional world, then the top view would look something like this. So we have our coordinate system, x and y, and an origin. This is, for instance, the inertial frame, the fixed one. And then if we look at the wheel in a top view, we see something like this, right? And here is then the center, and the wheel is rotating about this wheel axis with some rotational speed beta dot. That's the rotational one. And then, of course, the wheel also has some forward speed. And on purpose, I draw the forward speed, which is a vector v, and in this case, it's just x dot y dot, because we have here this position of the center of mass x and y. And on purpose, I draw it such that it's not aligned with the direction of the wheel. Meaning that in this case we have something like we have a lateral component or perpendicular to the wheel, this one, and we have a forward component, v, in line with the wheel. Of course, the wheel makes some angle with the inertial frame, the angle theta, because this wheel is essentially just a rigid body which has a position and an orientation in this two-dimensional space. Now, this wheel just slides along, right? It has this lateral velocity, and maybe the forward velocity does not comply with the rotational speed. Oh, I need a dimension here. I need a radius, r, because the angular speed times the radius should be this forward speed, right? So, and moreover, if you don't want slipping in the lateral direction, this one should be 0. This speed should be aligned with this body. So, for pure rolling, we can already write down what the conditions are for pure rolling. And say, let's start with no side slip. So no side slip, and then that means that this v perpendicular should be 0. And we'll find out what exactly the expressions are. And pure rolling, yeah, in the forward direction, forward, or in the longitudinal direction, then these two speeds should comply. So we have a speed v in the direction, and that should be equal to beta dot times the radius. And then it's perfectly, it has no slip, no brake slip or acceleration slip. Now, if we look at these conditions, these are conditions on velocities. So we could say these are constraints on the velocities. And actually, we are already very much used with constraints on the velocities, because our normal kinematic constraints, like a hinge or a point being connected, that was on the coordinates, but then we needed it on the acceleration level, so we differentiated then, we got a constraint on the velocities, and we differentiated again, we got it in the accelerations. But mind you, if we talk here about pure rolling, we start not with coordinates, but we start with speeds. We say this speed must be 0, that speed must be equal to that speed. So we start on a velocity level. And these constraints on the velocities have a very fancy name. Oh, I should watch, yeah. And the fancy name for it is a non-holonomic constraint. Super fancy. So that's apparently opposed to a holonomic constraint. And of course, Heike explained that all to you last year. You have scleronomic constraints and holonomic constraints and holonomic constraints. I have no clue. I always forget what they are. But it's just a nice fancy name. So whenever you hear about, oh, that's non-holonomic, then you immediately forget the word and say, oh, it's about rolling contact, apparently. Yeah. Now, who came up with the name? That was Heinrich Hertz. So, yeah, not so long ago. Heinrich Hertz was the first in mechanics who looked at this contact problems and this rolling contact. So, the inventor, in this case, the patent goes to Heinrich. Now let's be specific. So we have again, we have this figure, and I'm gonna try this. I love this actually. So I'm gonna zoom, and then I'm gonna copy and put it here. Yeah, a little bit smaller. This is so much fun. Okay. So here we have again this figure, we have the conditions, and now we have to translate these to our coordinates and speeds which we have in the figure. Well, that's not so hard, right? Because, zooming, it's always zooming. The sidewards velocity, which should be 0. Now what is the sidewards velocity if we look at the figure? So apparently we have to project our speed, right? So the sideward velocity, it's a projection of this speed. So that's the dot product of the speed, which is x dot y dot, and then in which direction? Well, if we have this angle phi here, then apparently there's here a director, a unit vector of the wheel, and the unit vector of the wheel is equal to, well, if I look at the picture, then the x component is minus sine phi, and the y component is cosine phi, right? That is the direction perpendicular to the wheel. So we have to take the inner product with this minus sinus phi and cosine phi. Or in other words, the answer is of course minus x dot sine phi plus y dot cosine phi. So that's apparently this perpendicular, this lateral direction, and that should be 0. So this is a constraint. Right? This is a constraint on no side slip. The next one is this v in the direction should be equal to beta dot times r. Now what is v in the direction? So then we need the vector which is in the direction of the speed. So that again v times, well, the direction of the speed is just simple cosine phi sine phi, and that should be equal to this beta dot times r, right? Or in other words, x dot cosine phi plus y dot sine phi minus beta dot r is 0. On purpose, I write it as a zero terminated equation. So clearly we have here two constraints. And how many coordinates do we have? Well, the coordinates for this one rigid body are x position, y position, phi position, and we have this magical beta, this rotation about its own axis. So together with these two non-holonomic constraints, apparently as a rolling body, this only has 2 degrees of freedom. And you can immediately imagine what they are. The wheel can move back and forth, and it can rotate about its axis. You can go anywhere. But what you initially think that, oh yeah, I can go anywhere with the wheel. Yes, you can, but you need a maneuver to come there. So if you say, I want to be there and directed towards the north, then you have to do a maneuver. Otherwise, you'll never get there. So that is the fun, actually, of the whole non-holonomic business. Now, to use it as a constraint, we like to formulate it as a constraint. So we define a thing called side slip, and slip is then in this case velocity, and we call it S1, and that equals this minus x dot sine phi plus y dot cosine phi. And how did I call it? Oh, the longitudinal slip I even forgot. And the other one you can define as the longitudinal slip or something like that. As 2, and that was x dot cosine phi plus y dot sine phi minus beta dot r. And it's actually beautiful if you define it like this, because for those who are doing automotive, they immediately think, oh, tires. Now I can add tires, because I have a beautiful definition for my side slip. Side slip speed, perfectly. So the only thing you have to add is some cornering stiffness, and you say, oh, side slip times cornering stiffness, oh, that's my lateral force, bingo, I'm in business. So you can easily connect a constitutive behavior to this. And also in the forward direction, if you want to saturate your longitudinal tracking force, then you can easily do that. Just look at the side slip. And okay, yeah, next step. So these are constraints, and we are used to deriving constraints in the following way. Now this one, and let's focus now on this one, on just this S1. The S1 we can write as a S, well, I should use a capital S, 1I times x dot I. And that is our notation actually. And then this looks like sort of a Jacobian. We know from the regular constraint this was a Jacobian. But what I'm now going to discuss is that it's not a Jacobian. I will prove it's not a Jacobian. How I'm going to do that? Well, I'm going to write down just this result. So the coordinates in our case, and let's forget now about the beta. I'm just talking, I'm focusing on this one. And you can imagine that we only look at the thing called a skate. So a thing where there's no lateral velocity, right? Here, this V lateral one. Yeah, so I say this is a skate. And a skate can move back and forth and not sideways. And I'm not talking about a rolling wheel. Just the thing is, I want to talk about just side slip. So I only take the coordinates x, y, and phi, because this body, this skate, does have a position and a orientation, angle phi. So those are those coordinates. And if I write it in this form, then I get here this vector x dot, y dot, and phi dot. Okay, what are the entries? Well, looking at the equation, it's apparently minus sine phi, cosine phi, and here's a 0, right? Yeah. And of course, if you want to add that constraint, you say s should be 0. So now what is the constraint on the acceleration level? So the constraint on the acceleration are, well, we just differentiate S1, of course, and then we get S1I x double dot I plus S1I comma J x dot I x dot J, in our beautiful notation. And how does it look? Well, the first part is very simple. S dot 1 is just copy what is here above, cosine phi 0. And here we have these speeds x dot, y dot, and phi dot. And then here I have to take these all these second derivatives, but there are not so many actually. If I have to differentiate this, the only variable which is here, x is not there, y is not there. The only thing is phi. So I only have derivatives with respect to phi. So the terms I get, this is a scalar thing. So the terms I get is x dot. And then times this one, and minus sine phi is minus cosine phi, right? So it's a minus sign actually, minus cosine phi, phi dot. And then the second one is y dot and a cosine, so again minus y dot sine phi, phi dot. So let's get rid of this. And those are these convective terms, or the ones which are quadratic in these forward speed. Now there's actually a nice way to write this. So I can write this as this Jacobian. I copy this cosine phi 0, and here I write x, y, phi dot, and then this is actually a double product. So I can write it as such: x dot, y dot, phi dot. Here's double dot, of course. And here also x dot, y dot, phi dot, transpose, oops, transpose. And then I just have to fill in this matrix to get all these quadratic terms. Now there are only a few, so that is, most of it is 0. So the only terms I have is actually, these are all zeros here on the diagonal anyway, here and here and here. And here I have only 2 entries, that's the minus cosine phi and the minus sine phi. And essentially this is this S1I, j. Now looking at this matrix, where one of the entries here is I and the other one is j, you clearly see, you see that the S1ij is not equal to the S1ji. The thing is not symmetric. Whereas, remember, in all the work you did up until now, if you derive all these second order terms, they were always symmetric. Well, in this case they are not. And that is actually the whole hallmark also of this non-holonomic thing. Because it means that one level up, if we take the velocity constraint and we say, is there a function which exists? So the question exists the following thing, integral of S1 and then with respect to t, let's say, dt, because we differentiate it with respect to time. And let's say we call that function f. Does it exist? Because if it exists and you differentiate f, you get your slip equation. And of course you can then go to the derivation, that your f dot is of course your S1 times the x dot, etc. And then you will see, oh yeah, but then I should get a symmetric Fij. And I don't have a symmetric Fij. Ergo, this function just does not exist. There is no primitive of this one. It's just a constraint in the velocities. And that's what we call a non-holonomic constraint. Okay. How do we deal with a non-holonomic constraint? How do we get our equation of motion? Well, actually, you just crank the same machine which we did in the past. Our equation of motion is we start with our virtual power expression, so AOM with non-holonomic constraints. So what do? You have your virtual power expression, you have applied forces, Fi, you have your inertia forces, accelerations, and you say, well, this virtual power, you have applied forces, Fi, you have your inertia forces, Siri, go away. And you say, well, this virtual power, you have applied forces, Fi, you have your inertia forces, Siri, go away. And you say, well, this virtual power, you have applied forces, Fi, you have your inertia forces, Siri, go away. And you say, well, how do I stop this? Any iPads? Help. Fi, you have your inertia forces, Siri, go away. And you say, well, how do I stop this? Any iPads? Help. Fi, you have your inertia forces, Siri, go away. And you say, well, how do I stop this? Any iPads? Help. Fi, you have your inertia forces, Siri, go away. And you say, well, how do I stop this? Any iPads? Help. Fi, you have your inertia forces, Siri, go away. And you say, well, how do I stop this? Oh, technology. How do I do this? Okay, so. Technology. Okay. Siri is gone? I think it's gone, huh? Okay, and Siri is gone? Yeah, to get rid of this. Here, server on. Yeah. How did I trigger that? Okay. All set. Okay. All set. Yep. Yeah, sorry for that, guys. I'm a bit clumsy with this. Okay, yeah. Virtual power and the expression, of course, times virtual velocities. And if, of course, the expression is this should be 0 for all virtual velocities which fulfill the constraints. So let's say for which virtual velocities? Well, we have this whole set of constraints. So say we have non-holonomic constraints now. Non-holonomic constraints. And the non-holonomic constraints in our case are just defined as this Sk being this capital Ski x dot I. Just in a velocity space, bang, these are the constraints on the velocities. And then we can add them, of course, with the Lagrangian multipliers. So we make a new virtual power expression out of this. The applied forces, the inertia forces, times these virtual velocities. And then we say, yeah, minus, that's just a sign convention. I mean, you can change also the sign of the Lagrangian multiplier, then you can write a plus. And then delta Sk, and that should be 0. Yeah, for all those virtual velocities, as long as they're not all 0. And of course, then we have to put in this equation in a virtual form. So copy this one, minus lambda k, and we get Ski virtual velocities. I should be 0. And now everything is with this virtual velocity I, so we end up with I equations. So I equations of motion being Fi minus Mij x double dot j minus lambda k Ski is 0. And you nicely see that those non-holonomic constraints are again pop up in the equation of motion by means of the Lagrangian multiplier. You can even identify what this guy is, because if these are speeds and this is power, then this should be a force, because force times speed is power. So this is clearly a constraint force. And in the case of our skate or our wheel, it's clearly this lateral force, which keeps it of having no sideward velocity. Of course, we have to add our constraint on the acceleration level. So we add our, we can first say Sk should be 0, and then we differentiate it that S dot k should be 0, or written out Ski x double dot I plus Ski comma j x dot I x dot j, these convective terms should 0. And these two now form our constraint equation of motion, which again we can write, don't zoom, don't shift. A little bit here, yeah. Which we can again write in this strange matrix vector form. So Mij I have here, and then I just have to look at this equation. I have a Ski, Ki, and my variables are of course x double dot j, and here I have a lambda k, and then on the right hand side I have the sum of all the applied forces. No, that should be a little bit bigger. And then here I have my constraint equation, so Skj, x double dot j, here all zeros, and here minus Skj I x dot j x dot I. And these are now my constraint equations of motion for a non-holonomic system. And if you look at them, you see no real difference with the holonomic constraint system. And the only difference is, of course, that the constraint we have is on the velocity level. So the next step is, if you now do your numerical integration, and let's assume you only have only non-holonomic constraints. So you say, given at time t, I know what the speed is and I know what the position is, right, of these guys. And then with my equation of motion, I find my accelerations. And now I'm going to do my numerical integration to find my next step. So what did we do? Xn plus 1 was the old one, right? Plus, and then we say the numerical integral of x dot n dt. That was our best, and of course this numerical integration is a way of writing it. It's an RK scheme or any other scheme you want to use. It's just numerical integration. Now the speeds, the new speeds, well, the new speeds are the old speeds, an approximation, plus again the numerical integration of these accelerations, and of course with a complex scheme. Now, which constraints do we have to fulfill? So, or in other words, are these okay? Huh? Is there any error? Well, there is no constraint on the coordinates in this case, so we say, yeah, the approximation is what they are. They're good. I mean, we have no extra constraints. How about the estimate of this one? Are they okay? Well, the only way to check is, well, just put them in the constraint equation. So you have to check, is my SKI times these approximations I, are they 0? And you will see they're not, of course. There's some small error usually. And then what do? If there's a small error, we use our Gauss-Newton process to correct for the errors. So usually it's something like epsilon, there's some error. And then with our Gauss-Newton Gauss-Newton process, in one step, and it's in one step because it's a linear minimization problem, because it's linear always in the speeds. In one step we can step back on our surface, because the equation we have is our constraint equation has this simple form: SKI x dot I is 0. Very simple, very linear. So the solution to that one is and if you should write a question mark, it's not 0, of course. And then with the increments, you can easily write, well, apparently SKI times my delta x dot, is my error here. It's my SKI times my slur. I need a slur. Oop, that's not a nice slur. This current value. So that is the increment you have to do. Now again, we cannot solve this because it's one equation with a lot of unknowns, but we have a solution to that. The increment is this Moore Penrose inverse. Shall I write it out? Yeah. So minus SKI transpose, SKI inside transpose, sorry, and this is power 1, minus 1. And so this is just the Moore Penrose inverse times this SKI and then the slur. But this is, of course, this is the error you'll have. And that gives you the increment, and then of course the corrected position is just this approximated one plus this increment, and then you're done. I mean, then bang, everything is on the surface. Yeah, this sort of finalizes the whole treatment of these non-holonomic constraints, and now I want to show a small example of this, and it's a classic example. And the example is called the Chaplugin sleigh. That's a strange word. Chaplugin sleigh. Now, who was Mr. Chaplugin? There was a Russian, and he was a teacher of Sadov. You can write about the dates and so on. It's more than 2 centuries ago, something like that, 1800, whatever. And Chaplugin was a guy also interested in this, non-holonomic contact, rolling contact, skating type of contact, because the mechanics of this non-holonomic constrained world is pretty complex. Whole systems like Hamiltonians and Lagrangians and so on, they do not really work for these type of systems. And it has to do that the constraints are on this strange, this velocity level. So for the pure mechanical physical guys, it was a bit of difficult, these systems are hard to understand. And even linearized dynamics in this system is still a very interesting topic. Anyway, and by the way, all rolling things are cool. I don't know how you developed in life, but when I was a very little person, I played with toy cars. And I loved it. I loved the way I had one toy car, and on the top you could turn the wheels, the steering wheels. And I loved to do parallel parking and making circuits and doing all kinds of things. And then you grow up, and then you want to have a scooter, and you want to have a bicycle, and you want to have a motorbike, and I mean, or a skateboard, or sailboat. I mean, a sailboat also is a sort of a non-holonomic constraint, right? Because in your sailboat you cannot boing move sideways. That's impossible. You also have to do parallel parking there. And it's fun in the summer to look at how people struggle with sailboats to park them. And that is, of course, because of the non-holonomic constraints. Yeah, people don't, well, maybe they're not so aware. But anyway, all systems with rolling contact are cool. Let's take some coffee.
In the quiz question,
I have to stop something now. Sorry. OBS. Stop recording.